So now we are going to be discussing hollow shafts. So we shall see that since the shear stress is small near the middle, remember we said for a solid shaft it will be like this. And near these ends, okay, as you move towards the center, the shear stress reduces. So if it reduces, then we will find that even as we actually go to the center, you will not experience any stress there. So if there are no other stresses, okay, under consideration other than torsion, then the hollow shaft may be used to reduce the weight of the machine components. So if we consider that there are no other stresses other than torsion, then this shear stress on the shaft, if it is only due to torsion, we can choose to remove some part of the center of the shaft and we make it hollow. So if it becomes hollow, we will be able to reduce the weight. That is a very important aspect of design, reduce weight. So let's look at a hollow shaft. It will look like this. So let us assume that the internal diameter is D and the external diameter is capital D. So the formula for polar second moment of inertia J will be, so our J will therefore equal to pi into D to power 4, this capital D, you get the external diameter minus the internal diameter, and then we divide it by 32. If you want to use radius again, then J will be pi out of 32 into 2 r to power 4 minus 2 small r to power what? Power 4. So this becomes pi times 16 out of 32, because now 2 to the power 4 becomes 16, 2 to the power 4 becomes 16. So into capital R4 minus small r4. So this becomes by 16, 1, 2. So this becomes J becomes pi out of 2 into r to the power 4 minus small r to the power 4. So we're going to look at an example. So we are told that a shaft has external diameter of 50 millimeters and internal diameter of 30 millimeters. It is 0.7 meters long and is subjected to a torque of 1200 Newton meter. Calculate the shear stress and angle of twist. So you can see here, we are going to be talking about a hollow shaft because it has internal diameter and external diameter, as you can see. So usually this is external diameter and this is internal diameter, a small one. So a small one is always the internal diameter. So let's look at the solution for this problem. So first of all, we need to calculate J, which is the polar second moment of inertia, and this is pi out of 32 into capital D to power 4 minus small d to power 4. So J will therefore equal to pi out of 32 into, this D is 50, so we are going to put it out of 1,000 to power 4 minus 30 out of 1,000. We are converting it to meters, so to power 4. And then we will find that J is going to equal to 534.07 times 10 power negative 9 meters to power 4. So when you compute this on your calculator, this is what you should get. So we will find tau. So tau is going to be, remember tau out of R is equal to T out of J. So meaning, if we want tau, this is going to be T, which is 1200 times what? Times R. R now is going to be, this capital R will be now the R max. So this is going to be 50 divided by 1,000. Then we are dividing that by 534.07 times 10 power negative 9. Remember, this R, you use the external diameter to get this R. So this tau, which is the shear stress, tau will equal to, so this becomes 56.17 times 10 power 6 Newton per square meters or pascals. Another one can say tau is 56.17 megapascals. Then the angle of twist. Theta, we said G theta out of L is equal to tau out of what? Out of R. So theta will therefore equal to tau times L divided by G times R. So tau we have already seen as 56.17 times 10 power 6. L is 0.7. G we have already seen as 90 times 10 power 9. This is gigapascals. Then times R, which is now 50 divided by 2 times 1,000. Or you just divide this 50 by 2 to get the radius. Then you divide it by 1,000 to convert it to meters. So finally, this theta is equal to 0.0175, and this is in radians. But in degrees, this will be 0.0175 times 180 divided by pi, and this is equal to 1 degree. So that becomes the angle of twist if you had a hollow shaft, and that would be the shear stress.